All right, couple of announcements. First, tutorial tomorrow, 1 o'clock to 3 if necessary. So Friday afternoon we'll be talking about the current problem set and we'll be good to go. What we're going to do is we're going to build on what we talked about yesterday. And that is rotation. Now, rotation falls into two categories. One is where you've got a system without torque. Without rotational force. And the more I think about it, with videos you can always go over like the morning lecture and see what I realized could have been done a little bit better. So in the afternoon you get something with a little bit more informed. Without torque and with torque. Without torque, it's just like you have no torque, so torque is equal to 0. If torque is equal to 0, then alpha is equal to 0. And what's the analogy that we use for linear motion? If you have no force, you have no acceleration. Just as if you have no torque, you have no angular acceleration. The thing will just spin on and on. Constant rotation. And sometimes, like steady motion, steady rotation, you may hear words like that. The big thing is that d omega dt is equal to 0. That the rotational velocity of the object remains constant. If this is the situation, then your theta will look like theta naught plus omega naught t. And omega is equal to omega naught. So without the torque, you know for a fact that this thing is just going to spin and spin and spin at the same rate it did forever, or has done, is doing, will do forever. In the other situation where you have torque, the torque doesn't equal 0, and the alpha doesn't equal 0. If you have something in a, and now what we're talking about here, because eventually we're going to get to torque bars, and that's a different weird thing altogether. With torque, you know this thing is going to, you'll hear phrases like spin up, which is the rotational version that I use for accelerate, and you have spin down for decelerate. The angular velocity changes so d omega dt is not equal to 0. And with something like this, you need to have your theta and angular velocity equations. These become theta equals theta naught plus omega naught t plus 1/2 alpha t squared. And omega is equal to omega naught plus alpha t. And in both cases, theta naught will equal 0. The reference position of where this thing begins to rotate, excuse me, where it begins to rotate will always be declared as the origin, so theta naught would be 0 at that point, and we don't have to worry about it. There will be one example later in the semester, in fact it'll be one of the last lectures, where theta naught won't be 0, and it will be the only time that we need it, and I will be the one using it. So in terms of tests, problem sets, theta naught is 0. It's just the initial position for reference. Now, with problems like these, they differ a little bit from the linear motion equations, the 2D motion, vectors, all that stuff. With the problems that we've done with test 1 material, it was a very linear, straightforward way of proceeding. Much like if I give you the recipe, you've got the ingredients, you just go step by step and you follow the pattern. With this, it's basically you have no recipe. You just have all these equations. Until now with this, what you're doing is you're taking these equations and you're substituting in more equations until eventually anything you don't know is substituted out until you get only one unknown. And then you solve for it. So it's a little bit more of a disorganized situation, but if you're prepared for that disorganization, you can actually figure stuff out. Now, with this type of problem, you just dump out the equations, and then you pick and choose. You kind of look for stuff that you need. And so you'll need things like theta equals theta naught plus omega naught t plus 1/2 alpha t squared, and omega is equal to omega naught plus alpha t. We had a few other equations that we looked at. One is the relationship between frequency and period. Another one, we have the relationship between angular velocity and frequency. We have another one where we relate velocity with angular velocity. We've got another one where we can just think about period as being the total time divided by the number of rotations. We've got also that the velocity of an object moving around in a circle can be the circumference divided by the period. So this could be rewritten as 2 pi r over period. We could have theta. The angle theta is 2 pi times the number of rotations. If it goes around once, that's 2 pi. 2 times 4 pi. Going over the list.
What did the capital R stand for?
Capital R, well, this, I could use it as little r. This is just the radius. I should be consistent, but.
And the N is rotation.
Number of rotations. And then when we have acceleration, the radial acceleration is v squared over r. I'll use capital R for radius for this particular time. And then the torque, which is the force times the distance, and I'll write dist just to make it different from d. Most frequently, it is the radius, but this is also equal to I alpha. And what we're looking at here is a list of commonly used equations that are used in these types of circular motion equations. The ones where the object is spinning up, spinning down, and the other one where you're just getting a constant rotation. What do you mean, this? Oh, this is the symbol for a fulcrum. And this is, let me draw it a little bit bigger. Hold on. That distance to the pivot, from the pivot point to the force, is the distance. Now, in the first example that we're going to do is object rotates 20 times in 30 seconds. What is the period, frequency, radial acceleration, omega, v at the edge, and alpha? And we're saying that it is constant angular velocity. The other thing that tips my hand with regards to, is this, yes? Okay. The other thing that tips my hand with regards to that the angular acceleration is 0 is that you don't see any mention of from rest. If I say the wheel spins up from rest, you know you're dealing with alpha equaling a non-zero value. Because it's constant angular velocity, d omega dt is equal to 0, and d omega dt is equal to alpha. So the value of the angular acceleration is equal to 0. Now with something like this, alpha is equal to 0, so if alpha is 0 and theta naught is 0, then theta is equal to omega naught t. And we also have that omega is equal to omega naught. So whatever we find for omega, it's going to be that value forever, effectively. Yes?
Okay, why is theta equal to omega naught t?
Theta is equal to omega naught t because theta is equal to theta naught plus omega naught t plus 1/2 alpha t squared. Alpha is 0, that goes away. Theta naught is 0, that goes away. Theta naught is always 0 because it begins, just as we say in two-dimensional motion that the origin is where the point particle starts, our orientation or angle of our rotating object, its initial point is the origin. The theta equals 0, or theta naught is equal to 0. Now we have the object rotating 20 times in 30 seconds. So from that I can get period. the total time t, little t, divided by n, which is 20. So 30 divided by 20, which is 1.5 seconds. Period is the time that it takes for an object to make one rotation. So this gives you the time for one, which is 1.5. Whenever you get period, you can immediately get frequency. So 1 over 1.5 is 0.67 inverse seconds, and the unit for an inverse second is hertz. Now that we have frequency, well, what else can we get? Well, we know the relationship between omega and frequency, 2 pi times 0.67, and that gives us 4.21 radians per second, or you could write it as inverse seconds. I'm fine with either one. So now that we have omega, and this is really like a very easy, you can think of it as a very easy Sudoku puzzle. You just sit there and you just track whatever you can solve, and if you can solve for it, write it down. I've got omega, so I could get V, which is omega R. The thing that I need for this part is that the radius of the disk is 5 meters. So omega 4.21, R is 5. That gives me 21.05 meters per second. The radial acceleration is v squared over r, the radius. I should be using capital R, but they're interchangeable, really. 21.05 squared divided by 5, 88.6 meters per second squared. And we use the idea that, or the unit of 1 g is 10 meters per second, so this is just 8.86 g's of acceleration. And so there is a very simple motion, circular motion problem where alpha is equal to 0. Now let's do something where the alpha isn't 0, where there is a force. Now when you see something like this, I'll generally draw it like this, and the thing that tells you that there is no angular acceleration is that there is no external force. If there is an external force, I'll draw it like this. The arrow with the R. And then I just draw a force, or FE, or whatever I call it. So if you see that arrow on a circle, also what I'll tend to say is omega naught is equal to 0 right by it. And so that gives it away that this thing's going to accelerate. This basically just says, I'll give you information that lets you know that it's already moving. So there's some obvious signals, or obvious hints that let you know what's going on.
So for omega over here, you have radians per second or inverse second.
Yes.
Is it wrong to use hertz there? Because it is still, it's the same thing as that just for frequency.
The definition of the way, I would prefer that you use this.
Yeah.
Because this is, it gets weird because technically a hertz, and this brings up an interesting point. Hertz is oscillations per second. And oscillation is also unitless as well. In a way, I think. And then in angular velocity, it's radians per second.
Okay.
So it's a different,
It's not quite the same.
it's not quite, yeah, it's not quite the same. Yeah, it's, don't do it on a test. Yeah, don't do that. Because they are different. In this particular case, we're going to have a disk of mass m and radius. Oh, I need to be consistent with this. I'm going to go, I hereby will always use capital R when it comes to radius for this problem. I go, it's at rest. Omega naught is 0. There is a force acting like this, and then I say how long does it take to rotate in times. And one of the things that you may notice is that for the most part, I'm not using numbers, which is definitely intentional at this particular moment. And this is because we need to understand how to do everything in alphabet soup mode. And this is one of the exercises that we do to show that the alphabet soup mode is way more valuable than the plug and chug method. When you're doing this, and you know you've got an external force, the two big equations that you write is the sum of the torques is equal to I alpha, and then you go, well, what kind of torques am I dealing with? We only have one external force, and if there's only one external force, there's only one torque. So that one force is F times R. The R is the distance from the pivot point to the edge, and then the force itself is F. We're dealing with a disk. Moment of inertia of a disk is 1/2 mr squared. So 1/2 mr squared is equal to Fr. One of the r's cancels, and I'm left with, oh, I forgot the alpha. Alpha 1/2 mr squared, because I is 1/2 mr squared. So I'm left with mr alpha over 2 is equal to the force. And I can now rearrange for any of the variables that I need, depending on what I'm given. In fact, what I typically do is I solve for alpha and just leave it like that. In the other equation that we use most frequently with something like this, it's theta equals theta naught plus omega naught t plus 1/2 alpha t squared. The origin of the rotation is 0. It starts from rest, which is also 0. So I'm left with theta equals 1/2 omega t squared. We understand that theta is equal to 2 pi n. We listed that on the list of equations. And just so you know, I mean, yeah, we're using a lot of equations. They will all be listed on the equation sheet. It's how you use them which is the important thing. So 2 pi n is equal to 1/2 alpha t squared. Now we're going to substitute that into here. 2 pi n equals 1/2 2f over mr t squared. what I'm doing is I'm solving for everything in terms of its various variables. And one of the benefits that we have is if you know how to do it generically, I would call this a core equation for when you're only dealing with a disk and one force, is that you can take this and solve for any of the variables in ft squared over 2 pi mr f 2 pi mr n over t squared m ft squared over 2 pi n r r ft squared over 2 pi n m, and then t squared 2 pi n m r over f, so t is the square root of 2 pi n m r over f. And with this, you can see that the main advantage of something like this is that you could solve for any of the variables. It doesn't matter. I'm trying to teach you, if you can solve it generally, then you obviously can solve for it specifically. So get into the practice of manipulating equations and being able to solve for any of the variables. Now, as an example, let's do this. And one of the things that was brought up to my attention this morning, they were asking, like, so what you're saying is there are multiple ways of doing this? And I said, yeah, you could do all sorts of weird different substitutions in order to get the job done. There's no one specific way. And in this particular type of problem, I've intentionally kind of left it to the student to just kind of use the equations and freestyle it and then just get to the one point that you need. Here we have a disk spinning up from rest. So obviously, the moment you hear spinning up from rest, you know that omega naught is equal to 0. At 15 minutes, the radial acceleration at the edge is equal to 20 meters per second squared. So at 15 minutes, or at t is equal to 900 seconds, the radial acceleration is 20 meters per second per second. And the thing I need... And actually, what I'm going to do is I'm going to intentionally, I'm going to show you how sometimes we can take a mistake and learn from it. And so what I'm going to do is, like this morning when I did this problem, I was just pulling masses and numbers just out of thin air to see if it could work. And so the mass of the disk is 1,000 kilograms. So what I'm looking for is, what is the question? What force creates this motion how many times did it rotate? Oh, no, wait. I think this is the one. This one works. Let's find out. So we've got a disc, 1,000 kilogram disc. At 15 minutes, the radial acceleration on the edge is 20 meters per second per second. It took 900 seconds to do this. What is the force on the edge, and how many times did it rotate in that time? It's a lot like you're pushing on a merry-go-round in a playground. What's the force necessary to get that thing spinning up to that radial acceleration in that time? And how many times did you go around the playground or spin around the merry-go-round? Well, the thing that you do with this, we've already done it. We've gotten a disc. We've solved for force. I've got force is equal to 2 pi mRn over t squared. And what we notice is, and if you were just given this, you would go through the same procedure to get to this. You notice that you have two unknowns. You have the force that's applied and then the number of rotations that it went through. So since we don't have this, we create our own. Theta equals 1/2 alpha t squared. And that goes to 2 pi n 1/2 alpha t squared. Now the one thing that is kind of that I'm going to do is n equals 1/2 1 over 2 pi alpha t squared. And what I'm going to do is I'm going to do another substitution. Oh wait, I'm kind of nodding myself up. Executive decision needs to be made immediately. And I'm running out of paper. Because the problem is that I'm kind of running around in a circle. So let's do this as we would do it on a test. Sum of the torques is equal to I alpha. Theta, which is 2 pi n, is 1/2 alpha t squared. That I alpha is equal to F R. Now the I is 1/2 mr squared alpha FR. Or mr alpha over 2 is equal to F. So I'm looking for F, but I don't know what my alpha is. So I can substitute in an alpha. 4 pi n over t squared is equal to alpha. And why is it 4 pi? Because I brought the 2 up. Yeah. And there's one last equation that we've seen it before earlier in the lecture, but I can't work it in because I haven't written it down yet. And that is that omega is equal to alpha t. That the final omega is equal to alpha times the time. We know that omega is 2. Oh, I know. V is omega. This final omega, oh crud, I'm getting all mixed up. So we have these two equations. And we could rewrite the radial acceleration as omega squared r. Or our omega is AR over R. So taking this, I know what omega is as a function of radial acceleration in R. I gave you AR, I gave you R, so 1 over total time is equal to alpha. And what I'm going to do right now is I'm going to bank, and by bank I mean put something into safekeeping, 1 over 920 over 5 is equal to alpha. 20 over 5 is 4. Square root of 4 is 2. So this is 1 over 450. And 1 over 450. I'm going to use this number as the alpha, but numerically it's 2.22 times 10 to the negative 3 radians per second squared. And that is the alpha. I didn't ask for it, but we're going to run with it. So now alpha is a known quantity. And 4 pi n over t squared is equal to alpha. Or n is equal to alpha t squared over 4 pi. Alpha, 1 over 450. T, 900. Or actually it's 30, or 900 squared, divided by 4 pi. Or 143.24 times. And this is one of the things, like if you looked at the notes from, and if you look at the lecture from this morning, I'm going in a different way. I solved for something else first and then went with it. If you compare the two, I'm going to end up in the same place, but much like how do you get to the square, where you could just go down University, turn left on South Lamar, and you're right there. Or you can go all the way to 6, go down to South Lamar, and then come back up. Either way, you end up at the same place. Now that n is a known, now I got to figure out how to get to my force. Well, I have an expression for the force, mr alpha over 2. The m is 1,000, the r is 5, the alpha is 1 over 450, and then we got the 2. So it's 5,000 divided by 900, and I end up with 5.56 newtons. So in situations like this, there is not a definitive one way of doing things. It's a lot like just building a Lego structure, and you have no instructions, you're just told to do it. So you fit whatever sticks together, and then you just go on from there. So that's an example of something like this. And now one of the things that I would definitely do in something like this is to write out take these lecture notes, write it out, and when you rewrite it, ask, what am I doing? And you may want to reposition the equations around so that it looks a little bit more intelligent. In the back, yes. Yeah, you could do all sorts of different things, yes. As long, now this is one of the things about like, I listened back to my high school geometry class and my teacher said as long as each move is valid, you can do all sorts of different things. In another example, what I'm going to do now is kind of gauging the time here. Is we have a disk and it's going to start from rest. Oh no, one of those again. But I promise it'll be a lot easier. So the mass of the disk is 20 kilograms and you have 4 balls which we can treat as just point particles. The mass of the ball is unknown. The radius of the disk is 5 meters. This force here is 20 newtons, and the time is let's say 300 seconds, and it made 10 rotations. So an external force is acting on this merry-go-round. There are 4 pegs of unknown mass on them. What's the unknown mass? Well, we've got a lot of stuff that we can play with. The theta equals 1/2 alpha t squared, because omega naught is equal to 0. And then 2 pi n is equal to 1/2 alpha t squared. We also know that the sum of the torques is equal to I alpha, and that is equal to the force times the distance from the point to the radius, or to the center. So it's FR. Things get a little bit different.
Do you need to define which way your force goes? Does it matter which direction?
In this particular case, no, I'm just saying generic rotation. There will be a point when I start talking about torque bars.
Right.
When that comes up, yes, it will be very
In
specific.
this case, your force could go down and your...
Yeah, in these types of problems, I'm not asking for, is it rotating clockwise or counterclockwise? Because it's kind of obvious.
Right.
So I'm more interested in the magnitudes of the whole thing. Now the total moment of inertia is the moment of inertia of the disk plus 4 times the moment of inertia of the ball. Because you got 4 of them. The moment of inertia of the disk, 1/2 mass of the disk, r squared, plus 4 mass of the ball, r squared. If the balls were placed in a different part of the disk, you would have to change that value of r to something, whatever it is, the distance from the center to its rotation. So that is the moment of inertia. And what we're looking for is that thing right in there. Now, what we can do is we can kind of determine what the moment of inertia is by taking this equation and rewriting it as I equals FR over alpha. I know what the F is, I know what R is, but I don't know what alpha is. But if I took this and rearranged it, 4 pi n over t squared is equal to alpha. If you just rearrange this, you can get this. And I'm going to substitute that into there, which means I get FR t squared over 4 pi n. F is 20. R is 5. T is 300, and I square it. 4 pi n, which is 10. So, excuse me? Yeah.
Where do you get the 1/2 in the moment of inertia?
The moment of inertia of a disk is 1/2 times the mass of the disk times the radius of the disk. For a point particle, it's the mass of the point times r squared. But since we have 4 of those points, it's 4 times the mass of the ball times r squared. So these are something like, this is defined, that is 4 times defined. And you get that. So these are going to be on the list of objects given to you at the test. So 100 times 300 squared divided by 4 times pi times 10. 71619.7 kilograms meters squared, because that's the units for moment of inertia. So now that I know the total moment of inertia, I could figure out what the masses of the balls are. So I'm going to solve for this. So now the only unknown that I have is the mass of the ball. The I, 71619.7 minus 1/2 mass of the disk, 20, times its radius squared, 5 squared, divided by 4 times 5 squared. So the mass of each of the balls is 714 kilograms, close enough in terms of the final answer. And so that is, there are dozens of examples of how you can work with this, but the procedure is still the same. I understand it looks confusing, but once you become familiar with A, the equations that you need to use, and B, be willing to do multiple substitutions, you can get all of this. The last thing I'm going to talk about before we end this will just take a few moments. We need to start using the terms momentum, which is for linear, and angular momentum, which is for rotational. So we're going to introduce 2 new terms. Momentum, P, is mv. So if you take an object's mass, multiply it by its velocity, you've got momentum. One of the things I always asked about is, where does the P come from? There's no P in momentum. Well, we're running out of letters. Mass is what's typically used for M. So momentum actually comes from the Latin word for momentum, impetus, or it's related to the word impulse. And so the P comes from those words. Now, angular momentum is called L. There's only one L in angular, so I don't know. I guess that's where the L came from. But L is I omega. So just as momentum becomes angular momentum, mass becomes moment of inertia, velocity becomes angular velocity. And the two things that are coming up that we need to pay attention to is the conservation of momentum, that the initial momentum is same as the final momentum, and the conservation of angular momentum. Li is equal to Lf. Now, the conservation of linear momentum is going to be useful for when we do collisions. So you get like two hunks of cookie dough and you slap them together. What's the final velocity? For the angular momentum, the best thing that demonstrates the conservation of angular momentum is we've all seen an ice skater when they're standing up on their tippy toes and they're spinning around. They have their arms out and they're spinning, and what happens when they pull their arms inward? They spin up. So what happens is that when they take their arms outward and they pull them inward, they're changing their moment of inertia. They're rearranging their mass. Angular momentum must be conserved. So if you decrease your moment of inertia, your rotational velocity increases in order to maintain the conservation. So last thing, tomorrow, 1 o'clock, Bishop, we'll talk about homework, and see you guys on Tuesday. It will be recorded and probably posted on YouTube sometime this weekend. We got one due right now.